Very good. So hello everyone. So welcome to the weekly seminar. We're actually going to pause for 2 weeks due to the Chinese New Year after this talk. So the next talk will be the February the 15th, and after the Chinese New Year. So today is a great pleasure to have Max Welling to give us a talk. And it's on the important topic, two important topics, deep learning and also deep learning for science or better understanding science. So I don't think Max really need the introduction. So I just say from top of my head. So Max is currently working, have two jobs, working for University of Amsterdam and also distinguished scientist for Microsoft Research. And so Max has done like many excellent. So nowadays, I think most of the people, when you write papers in deep learning, you can avoid citing Max papers, and so which is good. And so Max has been serving the community in many very diligently, being the program chair for many top conferences and win lots of awards. And I think those awards is just the names, but it's really the excellent work that Max has produced. Really help the community and influence the community and make a lot of young people to inspire a lot of young people to learn and really get interested in deep learning and machine learning in general. So so I will give all the time to Max. So Max, please start.
So thank you very much, Ping. So can everybody hear me? Can you hear me, Ping? Yeah?
Yes.
All right, fantastic. Maybe I should. Okay, so I'll start. So yeah, I'm gonna talk about sort of deep learning, a little bit of introduction, and our journey to introduce symmetries in deep learning. And then I'll talk about how to apply deep learning to the natural sciences. I'll just first minimize the this for a second. Oh. Now it's stuck. Weird. Okay. All right. So so these are all the wonderful people, students, postdocs, faculty that I've been doing the work with that I will be presenting today. I can't go over them all one by one, but you try to remember all the names. And of course, if you're interested in equivariance, there's a wonderful thesis by Taco Cohen on the right top corner, and there's also a good review article by Maurice Weiler in the right bottom corner with lots of beautiful illustrations, of which I will show a few. I'm going to talk about work from all these people. So the overview is so here, by the way, on the right hand side is one of these beautiful images that Maurice Weiler produced in his paper. So I'm going to talk a little bit about symmetries and equivariance, and then about graph neural networks, and then about how to sort of use graph neural networks to model molecules. Then I'll talk about PDEs, and then if time allows, I'll talk a little bit about quantum deep learning and machine learning, and then I'll conclude. So first, then the first part of this talk is about symmetries. Now, symmetries play an incredibly important role in physics and other sciences, natural sciences. For instance, it was known around the turn of the previous century that if you would have one observer here would observe an electric field, that this same electric field would be interpreted or observed by a moving observer as an electromagnetic field. So a magnetic component would be added purely due to the movement. And so this unified the theory of electricity and magnetism into one theory, the one set up by Maxwell, electromagnetism. Something similar happened for gravity. So when Einstein figured out that basically acceleration is exactly the same natural phenomenon as gravity, and equating those two, he basically derived all the equations of general relativity. And so these symmetry principles, basically relating one set of observations to another set of observations as being identical, and so there's a symmetry transformation between them, is an extremely powerful concept in physics. And we started to think about whether the same ideas could also be used in machine learning. And of course, there's also the standard model, which is sort of the fundamental model of all the particles that we know in our universe. It's very simple. It consists of leptons and quarks, but there's more structure. This is like a structured set of particles that are organized again in symmetry groups. So you can transform one particle in another particle by applying a symmetry group. So again, a unifying framework for quantum field theory. Now, symmetries in deep learning also exist. For instance, you could imagine building a classifier for a skin disease or a pathology slide like cells on the right-hand side. And you would know up front that if you rotate the image or translate the image, the class label would not change under that transformation of the input. And so that's also a symmetry. And so one question you can ask yourself is, if you would implement that symmetry, what would that mean for a deep neural network? So here's another beautiful image from Maurice Weiler's paper. And this illustrates the power of equivariance, basically first introduced by Taco Cohen and myself and Sander Dieleman at DeepMind in 2016. And the idea is actually very simple. The idea is, well, of course, we would be looking at flat images at that point. We have by now we have generalized everything to arbitrary manifolds. But the idea is that if there is a symmetry on your manifolds, in this case, there's an egg, and so there is one symmetry, which is basically rotation around this axis. So let's say we can apply the symmetry transformation to a signal living on this surface, like a image of a gecko. All right. And we have some operation inside our neural network, which is like a filtering operation. Let's say this is sort of edge filters. Then what we really demand is that if we first do the filtering and then the symmetry transformation, it should be the same as first doing the symmetry transformation and then doing the filtering. So it doesn't matter in which order you do these operations, you should always get to the same result. Now that's the concept of equivariance. And basically what happens if you do that is that you will build structure in your latent or hidden representations of your neural network. They're very much related to what Jeff Hinton calls capsules. So these are subspaces of latent channels in your neural network that transform sort of as a subspace, not mixing with other subspaces under certain symmetry transformations. And I'll talk about that more in a few slides. So they build structure, important structure into your neural net, and therefore they are an inductive bias. And if you have, apply an inductive bias, it means that you can learn faster from fewer data points. So the advantages are data efficiency. You can train with much less data in the same way that a convolutional neural network, which implements translational equivariance, is much more data efficient than a full multi-layer perceptron. Because if you have n neurons for an MLP, you would have n squared weights to fit. Of course, for a convolutional neural network, you would have, if you have like a 3x3 filter, you would have something like 9 sort of parameters to fit. And if you have multiple channels, of course, that multiplies. So the idea of these capsules, sort of these state of these sort of subspaces inside your hidden representations, is that they will represent the pose of an object. So there will be some encoding for the pose of an object, and the total activation of that capsule codes for the presence of an object. And I think that's a very powerful way to encode, the things that are at your input, and it will be very helpful to understand what's going on in the world. And of course, the third advantage is that if you build in this structure, then the next layer, if it's also equivariant, will have a much easier time understanding the structure that's happening in the layer below. Because if you rotate your input image and all the pixels get completely randomly permuted, then the next layer will have a very hard time understanding that that's a rotated version of the input. Now, another nice property of this sort of equivariance, this sort of closing of this diagram that I just showed, is that there is this property which we call abstractions preserve symmetries, right? So if there is some symmetry, which basically says that I have a face and I rotate it, right? Then you're on some orbit of your sort of symmetry group, and both of these would sort of map to an abstract face neuron, right? Then what you have is that if you would rotate them, then both of the rotated copies would also map to the same neuron, but now a rotated copy of the abstract face. And that's a very nice property again to have hidden in the hidden layers of your neural network. So formally, and this is very similar to what I just said, if I have a function f(x) to y, which is a layer, so convolutional layer, let's say, and I have symmetry transformations in the x space and the y space, so the input layer, let's say, and the hidden layer. And then what we want, so what we call f is an equivariant function, if first applying the function and then the symmetry, like here, will be the same as first applying the symmetry, but in another space, x space, and then the function, right? And it's important to note that this operation and this operation do not necessarily have to be the same. So I will illustrate that in this image, which is the illustration of what a capsule is. It's again, I think it's produced by Maurice Weiler. So here's a convolution that we would do for the group of 90 degrees orientations and translations, right? So we have a translation group, which means that we do a convolution. But then if we also want to have 90-degree orientations in them, what we basically do is we do 4 convolutions, but we rotate the filter over 90 degrees 4 times. And then we store the result in these 4 channels, which would then be our capsule. So that's what's happening here. So here's our input image. We have, let's say, some filter that detects eyes and another filter that detects a mouth. And then we have the same filter at 4 orientations. Then this we will call an eyes capsule. And the bottom we will call a mouth capsule. And if this image is straight up, then these are the filters that will fire. Now, if you rotate the input image, then the detections will also rotate relative to here. But what we see is that we also shift in this capsule dimension 1 to the right. And this is a permutation in this capsule dimension. So this basically means that the operation we are doing in the input space is not identical to the operation that we're doing in the latent space, but there is an operation, and the commuting diagram, that doing this first and then this, or doing this first and then this, still holds. So this is an equivariant operation. Now you could think if you just do a CNN, that this is the old videos from Jan LeCun's webpage, that maybe a normal convolution would already be equivariant. Why do we bother? But then, so here you see sort of a CNN and you see translations. Now, Jan LeCun already rotated the images, and then you can see at the hidden layers that they're actually not equivariant, right? Because you rotate and then something random happens. It's really, these edges are really trying to change. It's not just a rotated copy of the filter. And this is a sort of set of gifts made by Daniel Worrell in his paper on harmonic networks. You basically, if you take your input image and you rotate it in front of the camera, this is of course what the camera will see. And if you stabilize that image, you'll see this for normal CNN. In his paper, he introduces harmonic networks. You'll see that the stabilized image is much more constant than the one that you get from a normal CNN. So this is not equivariant. And this to a large degree is equivariant, although we would want complete stability. Now, we did generalize everything to continuous rotation groups, right? So I just talked about 90 degrees rotations. However, we did generalize everything to continuous rotation group for arbitrary angles. Now, what you have to do there is sort of do harmonic analysis. You'll have to look at what's called the irreducible representations of a group, and you will just have to include, say, the low frequency components of those irreducible representations. It's similar to doing a Fourier transform and just keeping the lowest frequencies around. And if you do that, then you see, for instance, that so here's the input, you rotate it, and here's the stabilized view. Of course, if you take the input and you stabilize it, nothing changes. Now, in the hidden layers, here's a scalar hidden layer where the output is just a capsule of a single number, not a vector. And you'll see that if you rotate it and if you stabilize it, it will indeed stay stable. Now, here's a vector representation, a capsule which is more dimensions, more channels. And you see that if you rotate it, you'll get some funny sort of movement of this sort of these vectors. But then again, if you stabilize it, then the whole thing will not change, meaning it's all equivariant. So that basically illustrates the closing of this diagram. Now, if this is feels a bit overwhelming, and but you want to use equivariance in your neural networks, I would recommend this paper. It's written by Mark Finzi. I'm a student of Andrew Wilson, and it basically lays out a very simple algorithm that will help you build an equivariance basis for your neural network. So you basically state the representations of the input and the output layer, and you provide the generators of the Lie algebra or the finite group generators. And once you provide those, the code will just tell you precisely what is a good equivariant basis for your neural network. And then you just take linear combinations of these basis vectors, and then your whole neural network will be equivariant. And what's kind of cool is that this algorithm is quite efficient if you, for instance, have a group with an enormous number of elements, like in this case, 10 to the 20 elements or so, but only a few generators, like Rubik's Cube group, then you can still compute all of the generators or all of the kernels, the equivariant basis elements. Okay, so one other thing I wanted to talk about briefly is we also looked at convolutions, equivariant convolutions, but in general, just formulating sort of a convolutional neural network on a manifold. And then you run into quite interesting problems that can again be solved by these considerations of equivariance. So for instance, on a flat space, if you take a kernel, right, and you move it to some other places, this is what you have to do for a convolution, right? You have to take a kernel and move it everywhere in space, take the inner product with your underlying image, and then store that in the next layer. In a flat space, you're in the fortunate position that it doesn't matter really how you move this kernel to the other place. It's always the same result. So you don't have to worry about the path that you took to this other position. How did you share that kernel? But on a curved space, this is actually different. So in a cube already, if I do parallel transport from here to here, or a parallel transport from here to here, you'll have a 90-degree shift orientation change for the kernel. And now you have to choose between the two. And then of course it can get very complicated because, what do you do here around this corner? And you have to specify precisely how you share. And that's actually quite cumbersome. Now, one other way to view this is to sort of cut open the space, then it's sort of locally flat, but you have these identifications of these boundaries here. So if I move through this here, I'll have to rotate if I go there. Now, so how do we solve it? So we solved it basically by putting a different frame at every point in space. So we basically acknowledge that we cannot actually get sort of a global frame everywhere that is consistent. And so what we basically say, well, in that case, we will just have to do with defining a local frame everywhere. So every point on the manifold has their own basis frame. But we then have to also tell, how do you relate the two frames? Right. So okay, so now here again is this example on the sphere, and also on on a Möbius strip. It's kind of interesting. If you move around it, it comes down flipped, mirrored. So, so the solution is to basically have, let's say for rotations, you could just have an irreducible representation of the rotation group here. So you filter, the filters, you make the filters equivariant on the rotations. And then you just tell me that if I go from here to here, I will have to apply a transformation on these filters, similar to the one that I discussed before, because when I move to here, my local frame has changed. And then if you can relate all pairs like that, then you can still define a global sort of convolution on a manifold. Now, this is not very detailed, and I would just recommend you to read the papers. Maybe the more practical implementation of this is to define a mesh. On a mesh, what we have is sort of a bunch of discrete points and flat surfaces in between. So in this case, let's say, if we want to do a convolution to point P, we look at all the neighbors in this mesh, and these neighbors are going to send messages to P. If you know about graph neural nets, and I will talk a little bit more about it in a minute, it doesn't care about these, for instance, angles or these distances. And so, but on a manifold, this should actually matter, right? These distances and these angles should actually play a role. And so the mesh CNN, which is a discretized version of the gauge CNN, does indeed implement this. And roughly speaking, the equations look very similar to a graph neural net, which is basically you look at some self interaction. Basically, you take your own activation at your own point and multiply by a matrix, and you collect sort of feature values for your neighbors and multiply them by the same matrix, and then you add everything up or collect everything, and that will be a graph convolution. I'll talk about more about that in a minute. So what we do for a mesh CNN is that we have this additional. So first of all, the kernel can now depend on angles and distance, and we have this additional row vector, which tells you how to transport a vector from A to B, right? So because first of all, you have to align the different tangent spaces, and secondly, the actual frames at these different points can be different. So you have to compensate for the fact that you have to parallel transport your vector over a manifold, as well as when you arrive, there might be a different frame in which things are defined, and you have to compensate back for that. If you do all that, then basically you can very nicely define a generalization of a graph neural net on a manifold, on a discretized manifold, a mesh, and that will be very close to sort of gauge CNN. Okay, now I'll talk about molecules. And so why are we interested in molecules, or why did I become recently interested in molecules? The reason is that molecules basically make up almost everything in our universe, unless you go to very high energies where molecules get broken up into smaller particles like quarks or plasmas when you go into sort of nuclear fusion reactor. There's also a couple of phenomena in the world that are not described by particles or by molecules, which is of course forces like gravity or electromagnetism or some nuclear forces. But except those, almost everything material that we look at around us is made of molecules. Yet, and we do know the equations for understanding molecules at a very fundamental level. The problem is that we really can't simulate them, and I'll talk about a little bit more of that in a minute. But that's basically because quantum mechanics is a sort of an exponentially hard problem. Now, molecules, or understanding molecules, are also at the root of solving many of our societal problems in health and environmental and climate science. For instance, if we want to design new drugs, we need to understand how two molecules bind to each other. If we want to build new solar panels, we need to understand how light sort of changes molecular structures and extracts energy from it. 20% of all the energy that we use is actually through friction. So if we understand how to reduce frictions through new lubricants, in fact, we can also make a huge impact on the environment. We need to understand molecules, for instance, to design better catalysts, for instance, for hydrogen production, right? So hydrogen um, is a hydrogen production is a process that is actually very inefficient due to the fact that you have to go over a high free energy barrier. And if you build a better catalyst, you can reduce the barrier and the amount of energy that you need to produce hydrogen. Nitrogen fixation is used to design or to produce fertilizers. It's also extremely polluting. A lot of CO2 goes out into the air, and better ways to produce uh, to do nitrogen fixation or to come up with better fertilizers is also very welcome. And of course, all of our biology is due to the interactions of proteins in cells, and getting a better understanding that would also help us fight disease. Now, in the sciences, let's say in particle physics or in radio astronomy, people build massive detectors, right? This is in CERN, one of these detectors there. I think it's Atlas. And in the sort of the radio astronomy, they built a square kilometer array distributed according in South Africa and in Australia, massive amounts of antennas which were all connected together to look deep into the universe, right? And so something like that we would also need for chemistry. And the way to do it, in my opinion, is to go for simulation. So the telescope, therefore, is actually more like a massive HPC cluster or sort of a cloud where we can do massive computations to look deeper sort of into the structure of matter. And so let me just try to illustrate that we are maybe looking at a new way of doing science. Well, it's maybe not new, but we are at the verge of being able to do much more in computers than before. So when we look at the design of airplanes, first we would just build things and fly them and see if they crash. Then we would start build models of airplanes and put them into wind tunnels and measure lots of things about it, and then based on that design our airplanes. These days airplanes are built in silico, just right into your computer, and it's just you just test them once you have already completely designed them and made sure that the whole thing flies. Now of course when you go in this direction, the amount of compute that you need increases exponentially. And the same thing happens for molecular design. So the first thing you can do is just, build a lot of molecules for, let's say, for a particular drug, and all test them to see if they are active. The next thing is you can do is you can create a lot of data around all these molecules that you created and build models based on that data. And the third one, you could sort of ab initio sort of data, which is you would simulate the molecules from first principles, which is basically using the laws of physics like quantum mechanics and Newton's equations. You just simulate the molecules, and from that you will design the drug that you're interested in. And again, you would need a lot of compute to do that. Now, the key challenges that we face in doing that is we need to improve the accuracy of the simulations, and that's hard because of quantum mechanics. We need to do faster simulations because the natural time scale for molecules to wiggle is about a femtosecond, and you'll wait forever if you want to do anything interesting on a sort of a more sort of a macroscopic time scale. But of course, the whole thing is chaotic. So chaos blocks us from really, doing this at a fine scale super fast. But then there are ways using machine learning to accelerate this. And then we need to go to much larger scales. And if we deal with billions of atoms, we may need to sort of do coarse graining and mean field types of approximations to go to much larger scales. Now, a molecule, of course, is just a bunch of atoms, and there's of course the electrons which are flying around, let's say in some kind of cloud. There's forces on the atoms, the Lennard-Jones for two atoms that are not connected, and then there's other forces on the atoms that are connected. And so under these forces, all of these atoms just wiggle and move around, and that provides the properties of these molecules. And that's in principle ruled, governed by just the old 17th century sort of laws of Newton, classical Newtonian mechanics, except for one of these forces. And this is the force that is coming from the electrons. And the electrons are so small and so fast that they really need to be treated with quantum mechanics. And quantum mechanics, unfortunately, is an NP hard problem to solve. And so here is where we really need to do the approximations. And it's a large amount of the energy is actually coming from the electrons. So one way to treat that is by force field methods. Force field methods basically try to approximate those quantum mechanical forces using a graph neural net. So basically create a lot of data that is coming from approximate quantum mechanical calculations, and use that data to then train a machine learning model, in this case a graph neural network, to predict the forces on the atoms as if you would do the quantum mechanical calculations. So we have a molecule, and then we have some graph neural network, and then they produce the forces, and then you will move the atoms according to those forces. Okay, so I guess the first thing I really need to do is give you a little bit of an introduction on what a graph neural network is, to dig a little bit into the details. I'll just do a little bit more detail now. And so if you know about deep learning, I sort of assume you know about deep learning. There's convolutional layers, there's pooling operations, there's nonlinearities, and then there's a final MLP that makes a prediction. So here's a convolution, but the nice thing is you can sort of interpret the convolution as a message passing scheme. So if you think about basically a convolution as all the neighbors, which could be vectors for the the vector elements are the channels, they'll send messages to the central node, and you also send a message to yourself. And then you do push it through a nonlinearity and then store it at the next layer. You can think of that as this message passing scheme as a natural convolution. Now on a graph, the problem is that the number of neighbors can change, and also the order of the neighbors is not really determined, unlike here where everything is structured. And if that happens, then in order to make sure that if I change the ordering of your neighbors, I will still get the same result, the simplest solution is to have all the neighbors use the same matrix to send that message to the central node. Now, you can generalize this slightly by actually formulating this as a general message passing scheme where you get an update for a message M from I to J, depends on the features at node I and the feature set at node J, some other fixed features at the edge. You send them through some neural network phi I, phi E to get your message. Then you collect all the messages from all your neighbors. And then at the node, again, you take your message, you take your local sort of fixed feature set and your local sort of transforming features, push them through a new neural network, and then store the result at the next layer. So this is a sort of more general message passing scheme. So the thing that we did for molecules was to say, well, we want to build in equivariance because we know that a molecule is equivariant if we rotate it. So the properties of the molecules shouldn't really change if we rotate the molecule around. So this is what we did here. So we have a molecule, we rotate it. This is the symmetry transformation. Sorry, this is the filtering transformation where everything changes, the positions change, the forces change, the scalar features change. But then if we rotate it, right, this is just a rotation of this picture where the forces rotate with the rotation of the molecule, but the scalar features will all stay the same. If I rotate it and then I filter, should be the same as I first filter and then rotate. So you can prove that these updates, which are just another version of these message passing updates, precisely maintain equivariance. So there's these scalar features H, there's the distances between the molecules, which are also scalar. Those go through in one function and create a message. And then there is another sort of vector, which is the forces, which has its own update. It's a vector update. and that will also change the positions using sort of Newton mechanics if you want. And then we do a collection of the messages and we do an update. So this is a direct generalization of this thing I wrote here, but now it's equivariant for those vectors. We did generalize this concept, but due to the lack of time, I'll just quickly skip through it. We did look at extensions which are not just vectors, but actual spherical harmonic embeddings. This is called the SE transformer because of the structure of a transformer. Later we did steerable EG and Ns, again using spherical harmonics, but now an even more general setup with equivariant MLPs as messages. You would have to read the actual paper to get more of the details. What's kind of cool is that you can sort of simulate. So these are the spherical harmonics on each node as we move through the layers, and you kind of see that it changes these spherical harmonics as it sends messages between all these nodes. And this thing is actually explicitly equivariant. So if I would rotate, the image, if you would rotate your computer screen, let's say, nothing would have changed, and you will see exactly the same things happening except then rotated.
Max, can answer a naive question. So the molecules are equivariant. Is that an assumption or that's a physical law?
Oh, that's a physical law, right? Because if you would just rotate the world around, which would be sort of equivalent as rotating, your head, let's say, as an observer, we want that the physics is just a rotated version of the physics described by sort of the other observer, which is standing straight, right? So that's just a physical law. Now, of course, if you would have, let's say, a magnetic field that would be pointing upward or a gravitational field pointing downward, and you would rotate the molecule inside this gravitational field, but you wouldn't rotate the gravitational field, of course, then things change, right? So that will break the symmetry. But in general, the properties of a molecule are invariant to in which orientation you describe them. Now, that's not obvious if you just write down actually your graph neural net, right? But if you just write it down, you have to choose some input orientation. And it doesn't automatically mean that if you rotate your input, that then you will also get a rotated output. So you really need equivariance to maintain that.
Thanks. Yeah, we actually have some friends from a physics field. I'm curious if they have any comments on this. Jiangping, if you hear me, are you able to give a comment? Yeah, Jiangping is actually the deputy dean for Chinese Academy of Physics. Yeah, he's in the audience.
Yeah, I actually thanks for asking me. So actually, so in the molecule, there's only a few different atoms, right? So let's carbon, hydrogen, or sulfur, whatever. There's so some positions, like if you are seeing atom, some positions, maybe they're also equivalent, equivalence. So do you consider that or not?
Do you mean the position, so the permutation of the atoms, right?
Yeah,
so
yeah.
if you
Yeah.
So that's a very good question, because a graph neural network will take automatic care of this. So in a graph neural network, of course, you have to choose an ordering of your, a labeling of your atoms or your atoms, basically. But the graph neural network is automatically equivariant under relabeling the particular atoms in any particular order. So it does mean that since you describe two identical atoms by identical features, if you swap them in this input representation, and you already know that the whole thing is equivariant to label swapping, you'll get exactly the same answer, but then just the labels swapped, and you'll just get exactly the same answer. So it's automatically included in this framework. So in some sense, you could say these things are equivariant to permutations of the atoms, as well as the geometrical sort of rotations and translations.
Thank you.
Can I move on?
Yeah.
Okay. So Okay, so the next topic I want to quickly talk about, because I also want to cover PDEs quickly. So the next topic I want to talk about is equivariant, sort of normalizing flow. So basically normalizing flows are a generative model. So this is different than I just described. What I just described was an input mapping it to properties. Now we're going to do sort of generate molecules, from out of nothing, right? Just build a generative model for molecules, perhaps conditioning on certain properties, right? So the idea is a normalizing flow. You start with a simple distribution and you will apply a sequence of invertible transformations to then produce the the points on a more complicated manifold. And here you sort of see the steps that you can take. And this has to be invertible, so you have to be able to go back. And if that's the case, then you can write down an analytic expression for the log likelihood. So the way we basically do it, so the way you think about this is that you generate a number of atoms and including their types, which are the colors, and then you have some flow set of transformations which transforms this slowly into a molecule. And you have a data set of molecules, and then you train these flows to, out of noise, basically generate the actual molecules. So that means we both generate the type, so we can change the type of the molecule as we go, but we can also change the, of course, the positions of them. I'll skip this. I'll show you this maybe. So all of this is equivariant again. So if the molecule, we can rotate the molecule around and has exactly the same probability of being generated, right? And this is the inverse flow, which you basically make it into sort of a random set of atoms, and then here it gets assembled back into a molecule and it gets rotated. So these days, so this is actually something we are currently writing up, and so I cannot give you the details yet, but this is a diffusion-based model, which actually happens to work a lot better. All of this is based on this equivariant graph neural network that I described. And we can now generate molecules which are already quite a bit bigger to high accuracy. So we can generate highly stable molecules that are realistic and have quite a few atoms in them here. So we're making fast progress in this. So the last topic I want to talk about, I think within the time that I have, is solving PDEs with graph neural nets. So this is a new application area. There's a lot of activity. And of course, in the sciences we describe are basically our models mostly with partial differential equations. Now the solvers for these partial differential equations are actually quite slow and cumbersome. And so one way is to think to amortize that computation using a neural network. So basically the idea is to look at lots of solved PDEs and then train a model to solve new PDEs for you, but much faster using your neural network. So PDE basically is sort of a constraint, if you wish, on a feature field U as a function of X. You say that the time derivative of that feature field is equal to some function of time, position, the field, and all its spatial derivatives. Of course, there needs to be an initial condition and some boundary conditions as well to make it well defined. And there's special cases which are based on conservation law, which looks like this. You can write them as ddt plus and then the divergence of some flux J that has to be 0. So this basically means that if you use Gauss law, it means that the amount of stuff that moves into any cell sort of minus the amount of stuff that moves outside of that cell has to be the same, right? So it basically means that you cannot create or destroy stuff inside a cell. That basically whatever goes in has to come out again at some point. So you could, I guess, move around in a cell and then it would sort of increase the amount of stuff inside a cell, but at some point it have to come out again. So the amount of stuff has to be conserved. So the PDEs that we train are what we call autoregressive solvers. They are precisely what you would imagine. You would have some data set where you have a sort of a sequence of U's, which is the field that you're interested in. And you would try to predict using some function A, which is your neural net, basically from a given field U and a dt, a change in the time step, you want to predict the field at a future time step. And you just generate lots of data, these types of pairs, which you have in your data set, where you look at the prediction, you compare it to the ground truth, and you have some loss function, and you do back propagation on that loss function. Now, there's a whole bunch of tricks which really help improve the situation. One is temporal bundling, which has to do with the fact that you don't just predict one time slice in the future, but you predict a whole bunch of time slices into the future in one time. There is another one, which I haven't written down here, which has to do with adding noise in the right amount of way. So you have to add noise to make this solver more robust to, drifting. It does drifts away from the solution. You want it that to be robust against that, and you should sort of add noise in a particular way to battle that. I won't discuss, show you too many equations, but the idea is, again, we have some graph neural network which represents the sort of spatial integration nodes, the places where you collect information on the plane. We have basically some time sequence. We create some features using an MLP. We then put these features on a graph neural network. They exchange information spatially using a graph set of equations, and then we do convolutions again over time to create a new set of U's, which is the field U that we predict. We then push that back into, the sequence. So we shift forward, we put this back into the sequence, and we push through the whole thing again. And so that's how we predict future U values. So these things work amazingly well, and starting to work increasingly better. So here's Berger's equation, which creates shock waves. So here is a position X, and here's the field U, and the color is time. So we go from the blue to the red. And over time, you'll see this PDE creates this shock wave. And that's pretty hard to do for a neural network, but these types of neural networks that we train based on GNNs do this beautifully. You can also generalize to new PDEs, which is kind of fun. You can start with sort of one PDE and train on one PDE, but then change the parameters of your PDE a little bit and then test on another PDE. And it will still do surprisingly well on this new PDE. So you can transfer a model learned for one PDE to a new PDE. We've done it on two-dimensional Navier-Stokes equation. You can also integrate that. And these are the latest results, which haven't been published yet, but this here we use symmetries to do data augmentation. So you can all these PDEs, they have lots of symmetries embedded in them. You can use those symmetries to create from one data set a much larger data set, basically for free. And then you can train on this much larger data set. And what we found is you can now roll out for a very long time. So for a sort of 400 time steps into the future for these trained models, and it stays very stable, right? So you can see that ground truth and actually generated neural PDE solvers are now basically on par for even for distant future predictions. So this is a very exciting development, I think, and of course they are much faster this way. I think we'll see a lot of development in this field. I think I'm kind of running out of time a little bit, so I'm going to skip this. So this is about irregular grids, how to deal with them, running a PDE basically on your neural network, and then moving into quantum a little bit. I'll just skip that because I think it's probably a bit too technical for now, except for maybe saying that we did, in the process of looking at this, we did actually discover particles in our quantum neural networks, and we call the particles Hintons. So you can really think of those as particles which are floating around in a quantum neural net. Of course, this would be in a quantum computer and not in a normal neural network. Okay, so to conclude then, so I think we'll see the application of machine learning to scientific computation in general, and to quantum chemistry and condensed matter in particular. This application, the applications that are coming out of this are extremely exciting, in my opinion. We can start to tackle problems and challenges in sustainability, like carbon capture and hydrogen production and producing green fertilizers or biodegradable plastics, as well as in health, new vaccines, new antibiotics that are protective against resistant bacteria, or immunotherapy against cancer. And so there's a huge promise of these techniques to basically help us address some of the core challenges that we are facing. And I think this is a very good time to work on these problems because there's a convergence of technologies that are starting to enhance each other. So there's, of course, machine learning and deep learning, which are making a strong impact in these fields. There's the massive scale cloud computing, which is at a point that it can really do very large scale computations. In 10 years or so, we'll have quantum computing to add to this mix. And one of the most exciting applications of quantum computing is, of course, in chemistry and in computational chemistry, because what better to do with a quantum computer than to simulate quantum mechanics of nature. And finally, there's also automated and high throughput experimental testing, which is completely roboticized in factories, which is also developing fast. So I see there's going to be a massive spur in activities in these fields. And hopefully this will create new ways to design new materials and new drugs. And with that, if you're interested, we are opening a new office in Amsterdam in this direction. And let me know if you're interested in this. So thank you very much. That's the end of my talk. I'm about on the hour.
Oh, thank you. Thanks. Thank you, Max. So everyone in the audience, so this is excellent opportunity to ask Max some questions. Yeah, so please, so we don't have to leave and until Max decide that he has to run for his HTML submissions. But yeah, any questions from the audience? So Professor Arduino, I see you in the audience. Thank you for coming. So do you have any comments or questions or suggestions about the PDE solvers?
Yeah, being fascinating. I'm a professor. I had the pleasure to be the one that brought Pingley to the United States 25 years ago. So Max, excellent presentation and really eye-opener. I am a civil engineer, and what I do is to solve differential equations either for fluids or for solids. So Navier-Stokes equation is a natural one, but also for solid problems. And the application of this type of solvers that speed up the solution would be excellent. Right now we are using particle methods, and when we go to a supercomputer, we can go to maybe 10 million particles, but we always reach a limit that is given particularly for the time. So any application of these to PDEs is incredibly useful. Thank you.
Yeah, it would be fantastic to see, a wide range of application areas for this. So yeah, what I also find interesting is that these neural solvers can actually interpolate perhaps between particle solvers and fixed grid solvers, because the positions of the nodes of a graph neural net, they don't have to be fixated. In fact, you can also optimize over those positions. And so you can then sort of start to treat them as the particles which are moving around as well while they're doing the computations. But yeah, so I think there's a huge amount of development still to be had.
Yeah. So how do you see the future? Do you think that engineering schools are going to start? Are we going to stop using differential equation solutions? What is going to happen with all the calculus that we teach to our students? Is going to be replaced by this?
No. I don't think it's going to be replaced, but I think you can expect to add machine learning to the curriculum. Right? I don't think it's going to be replaced, because in fact, we to train these things, we do need the traditional solvers as well.
The traditional solvers. Yeah.
So I think all of the I see much more into hybrid methods. So in the sort of traditional solvers, you can put a lot of inductive biases about the system and how to integrate things, et cetera, et cetera. But then
It's
machine
4.
learning is in some sense just amortization, right? It's just in some sense doing a lot of computations, but not throwing them away. So storing the results of these computations inside the parameters of a neural network so that next time around you can integrate faster. So in that sense, I really think we really have to look for hybrid solutions.
Yeah, it's interesting. At the University of Washington, we are just starting a new center for AI and ML in the engineering school. So that is going to permeate to all the different units. So all the units have to develop curriculum on AI. And so it's interesting, big push by the central administration to improve in this area. So yeah, looking forward for the future. Thank you.
Yes, great, thank you.
Thank you, Professor Arduino. So any more questions? Any other questions?
I have a question. So actually, I'm very interested in this Hinton you mentioned, this virtual particle. So, but when in physics, we talking about a particle, usually, some properties categorized by like spins or whatever, these things. So what kind of characters, for these virtual particles in the network, new network, you can think to classify them?
Right, so it's a boson.
Uh-huh.
It's not a fermion, that's a boson. But it's yeah, so spin, I don't think, I think you can actually produce spin. You can define spin, but that would have to be if you sort of add symmetries and equivariants to your neural net, right? So as in physics, you could argue that spin is a representation group of the is a representation of the rotation group. So if you make your neural network rotation equivariant, you create capsules, the way that I described, and these capsules are basically the internal dimensions of your particle in some sense. And you can sort of create spin, I think, in that particular way. And we didn't go that far. We basically, we define fields, scalar fields, basically, which are basically the, how do I say, the amplitude of a sort of a scalar field. That's and we make that quantum. And so we will just have the simplest possible particles, which is sort of spin zero bosons. But I think you can become much more sophisticated if you want, and create internal sort of dimensions.
Is the statistics can be well, like these quantum statistics, like boson, fermion statistics, can well defined in the network or not?
Yeah, I think so. Yeah, so I think you'll literally, basically what you do is you create creation and annihilation operators in your, it's literally just doing quantum field theory, but you basically, you have fields, you have a field, and then you have the sort of momentum field, you have these turn into operators, you let them act onto Gaussian states, sort of coherent Gaussian states. You define sort of linear operators on those, which are rotations and scalings and squeezings and stuff like that of these states. You also define a nonlinearity, which you can define as a unitary transformation, but which looks very similar to a ReLU type of nonlinearity, although it's a little bit softer. And you can just do a rotation of your basis, and then you create annihilation and a creation operators, and so you can then go to a Fock space representation, and there and so it's the symmetric part of the Fock space basically, and you'll create bosons that way. So it does satisfy the sort of the statistical exchangeability relations, or the symmetric relationships. But of course, it's, you can think of this maybe more as, the bosons you would create as a quasi particle in a solid state, right? In a solid or a condensed matter, right? So that's maybe the best analogy. If we would actually create this neural network, then I think the best analogy is to think of this as a piece of condensed matter where, you have phonons and stuff like that flow going around. And that's what your particles, that you describe that basically by particles.
Thank you, Jiangping. Hey, more questions?
Yeah. Can you hear me?
Yeah.
Yeah. Hey, Max. It's Ming here. So since we talked about bosons, so I wonder if there's any like modern versions of the Slater determinant for fermions, because Slater determinant has like a n to the third order of computation. So I wonder if there are any cheaper versions of that in the modern like symmetric neural nets, like anti-symmetric neural nets.
Yeah, we haven't really looked at that at all. So yeah, I couldn't really answer that, to be honest. But no, in our case, we basically really tried to start from a convolutional neural network layer, and then you sort of end up in this particular quantum field theory with bosons. We haven't thought about fermions. I mean, I guess you could sort of add fermions if you wanted to, and think about, how you could compute with them. And but then you also have to think about how you would create them somehow in a quantum computer. So for us, what's nice about this particular sort of quantum algorithm was that it maps very beautifully onto a photonic quantum computer, right? So actually in China, I think they're very good at building photonic quantum computers. They have the state-of-the-art results in these quantum computers, this type of quantum computer, right? That is optical. And so this architecture maps almost perfectly onto an optical quantum computer. And in optical quantum computers, they have these bosons, right? So they use bosons, boson states, bosonic states, basically. So I don't know how to add fermions there and what that would mean, practically speaking, right? I don't know, but I'm sure there's going to be interesting developments there somehow, but I have just not thought about it.
Yeah, hopefully we'll see new developments soon. Thank you.
Yeah.
Thank you, Ming. Other questions? No more questions? Don't miss this excellent opportunity. Well, I guess a lot of people are anxious to going back to the SML submissions. So, so let's all thank the speaker. Thank you, Max. This is a wonderful talk, and we look forward to your physical visit to Baidu and China at some point. Yeah, my office is actually in Bellevue, Washington. So I'm now sitting in Sunnyvale office. It's kind of complicated, but thank you. Thanks so much. And
yeah,
thank you everyone for coming.